Good. Anything else? The bureaucratic nature. Anything about what we talked about last time? What did we talk about last time? What are we doing here? What is the point of all this?
Scattering.
Yeah, why do we care about scattering?
So it helps us, I guess, figure out a limit to the size of the nucleus.
That's where we're headed momentarily. Ultimately, that's what. Oh, thank you. I'm sorry.
I meant to slide it closer for the read.
I had no idea what the heck was going on there. It's like, it suddenly, wait a minute, I put it over there. Got it. All is well. It's the only game in town. It would be lovely if we would just have a really good microscope and, you know, keep turning that knob till we home in on the nucleus, and it just doesn't work that way. Only game in town is banging stuff together. And chemists have a certain, I mean, they do great work and I love what they do. The chemist came and gave a talk and said, you know, physicists know a lot of stuff, chemists make a lot of stuff. And that's words to live by. But they have an advantage in that when they have a bunch of electrons and protons and neutrons moving around and doing stuff, they move here and they move there, they have the same number of electrons, protons, and neutrons at the beginning as at the end. One of the things that's going to happen to us is, for reasons that make a lot of sense, we're going to try to bang these things together harder and harder and harder. That's like turning up the zoom on the microscope, banging them together harder. The problem is eventually we're going to start making new stuff. The energies are going to be so big that we're actually going to make things that weren't there to begin with. So that makes life that much harder. Chance to learn new stuff, but that's a problem that we're going to run into. So we need to understand what happens when two things bang into each other, and we're in the middle of doing that. So our lab is stuff over here, things that we can get going in this direction to bang into it, and then the detector, we can figure out where they come out, and we're going to figure out what that can tell us. Turns out it's a lot easier to think about this in the center of mass frame. Who knows why? What's the total momentum in the center mass frame? Zero, always zero. Yeah, no matter what. You don't have to know the details of what's going on there. To know the total momentum in the lab frame, we need to know the masses and velocities of all the particles. Well, what do we not know the masses and velocities of? The particles. So it's actually much nicer to be in the center mass frame. Unfortunately, we can't work in the center mass frame. We have to work in the lab frame, and the lab frame is where we started. We went to the center mass frame, we did a bunch of stuff, and we came back out, and now we're about ready to look at what our detectors can tell us. That's where we are. I think we have this. Start again. Anybody seen that before? Getting some heads nodding. I don't know if they're just trying to be nice or if they really have seen them before. I think, according to me, that's where we were. That's not where we were. You got to help me figure out where we really were. Well, so that's the velocity of the impacting particle, the one that we know is moving and we know how to detect. So that's the one we care about. We know where it came from. We can detect it, and so we can put a detector and see where it's coming out. We're going to see why we care where it's coming out later. But the direction of this object, let me draw this. Lab frame, that particle's going that way, stuff happens, it's coming out that way. That angle I think we called psi before. I remember writing down psi before. That was the angle that beam makes with the original direction. So I know what that is because of the way I set up my experiment. And so now I can start moving my detector around to see. I would love to know the tangent of that angle psi. How would I get that? Given that the particle is moving in the direction of V prime.
Capital V prime.
It is capital V prime.
That's the ratio of the y
Yeah,
magnitude of the
I'm,
maximum.
yeah, I'm ready to go, right? From my model, I have the opposite side and the adjacent side. So the tangent is just gonna give me that. Notice that is in terms of an angle scattered in the center mass frame. Remember, that was what theta was. Theta was the angle in the center mass frame. But this is what I can measure because this is what's in the lab frame. I want to know if there's a maximum scattered angle. So I can sit here and put my detector. We talked about why I don't want to put it here, right in line, most of the time. Even if I care about what's scattered in the forward direction, that's hard to measure. So I move it away, and I can move it anywhere I want to around here. I can also move it around this way. I typically won't, because a lot of things don't matter. They're what is called azimuthally symmetric, and we'll talk a little bit about coordinate systems eventually. But because of the setup here, I expect it to be the same here as here, as here, as here, as here. And I think that's sort of intuitive, and I'm not gonna belabor it too much. You almost always measure this. So how is that side changing, not what's happening around that? I'm not saying never, but generally speaking, this is certainly where you start. I wanna know if there's a maximum. Who knows how to find the maximum of a function? Just me. Okay, 2 of us. Okay, 3 of us, thank you. I was hoping your hand would come up. How do you find the maximum of a function? Got to take a derivative, right? That's what derivatives are for. They're probably more than that. I'm going to let you show that when you get done, again, I have no dog in the fight about how you learn take derivatives, but know that that's the job. Can secant be 0? Turns out it can't. Make sure you can figure that out, right? Make sure you can say what that is. Matter of fact, just for grins, this is just kind of an exercise in how to do stuff, but we're not going to use this at all. But this is going to make you remind yourself of some stuff that you probably know, but don't have right at your fingertips. Turns out that number can't be 0. Because secants just can't be 0. That's automatic. But I would say it's worth your while to know how to do that. If it's really, really hard, that shows you, oh man, I better work on that a little bit. If it's dead easy, it won't take you that long. You just do it. So this can't be 0. So the only way this side is 0 is, this whole side is 0 is if that fraction is 0. Everybody with me? And that is only 0 when the numerator is 0. So I already know that I'm gonna have a maximum when cosine theta equals minus r. And so I can now figure out what tangent theta is, the maximum tangent theta. Where are you at? we are actually interested in the case that are really, really small. And that's because that's what Heisenberg, Rayleigh and those guys were thinking about when they were looking at scattering of helium nuclei, the cannonball of these very light, solid, thin layers of gold. Okay. So that tells you what about that maximum scattering angle? Tangent theta, r is really, really small. Tangent psi is really, really small. What does that tell you? Anybody remember? Well, do this. Somebody tell me how to plot tangent of psi as a function of psi. Where do I start?
Zero.
Start at 0, 0, origin, because when psi is 0, tangent is 0. That's at least a starting place. Now what?
It kind of looks like x cubed.
It's going to start going up. It's not as flat as x cubed, because it does have an initial slope, but then it's going to be asymptotic at pi over 2. But if I'm right down here, what does it look like? If I look at a tiny little piece of any function, what's it going to look like? Straight line. That's a straight line. It's going to be linear, and it turns out it has a slope of 1. Tangent theta, psi, is about equal to psi, one side is small. Small angles tangent is about the same. Same for sine. But only if you measure theta in what? Radians. That's why we're stuck with radians. We like to say this. We also like to take derivatives. If you can take a derivative of a function, of a trig function, it's got to be in radians. So that's kind of why we do radians most of the time. So since the tangent is really, really small, we know the angle is really, really small. And so what does that mean? That means that I'm going to see some good, reasonable amount of scattering here, but when I go back over here, I don't expect much. And this is a really, really big thing that's almost intuitive, right? It's a really gigantic cannonball going at a piece of tissue paper. Yeah, the tissue paper is going to have some effect. It's going to move a little bit, but I really expect most of the deflection to be small angles right around there. Now, because it didn't cost him much, grad students are cheap, he said, go ahead and set up your detectors behind it just to check for those high angles. He didn't expect to see anything, but you're there, you're doing the work, go ahead and make those measurements. And sure enough, he saw these really big angles scattering back. And that was very, very surprising. I kept saying Rayleigh scattering, it's Rutherford scattering. Very, very surprising. So their model of matter, they at that point knew did not work. They knew they were wrong about the structure of matter. They had to work on it to figure out what it was. And we'll talk more hand-wavily about this. Well, one of the things we've talked about, what have we said about the interaction between the incoming particle and the target particle? What have you said about that interaction? Was it electrical? Was it gravitational? Was it? Who remembers what we said? Good, because we didn't say. If you remembered it, it would be a problem. We didn't say what it was. And you say, well, then it doesn't tell us anything. No, exactly the opposite is true. Everything we've said so far does not depend on that. Those are called robust, scientifically robust conclusions. If your conclusions don't depend on the details of the interaction, that's awesome, because now you don't need to know what those details are. On the other hand, you can't tell about the interactions. So you would like to measure something that tells you something about that interaction. But so far, we now know that the model that they had, the so-called plum pudding model, where you had these very, very, thin, very, very small charge density, very small masses with these big cannonballs going into them. We now know when those big cannonballs came back at you off a piece of tissue paper, there's something going on in that tissue paper. this was the first picture, the first idea that, oh, there is a big bunch of matter in the middle and a whole bunch of nothing around the outside. That's what the Rutherford scattering told them. They didn't know any more than that, but that's already pretty awesome, right? That's already a lot more than they used to know. So, in my original, I talked about, we decided I dove into the electrostatic interaction. Not gonna do that. We're gonna talk about something called hard sphere scattering. It's a little bit easier to follow. We can get all of the right ideas in, including some that are not in electrostatic scattering. And then I'm just gonna kind of wave my hands and show you some pictures about what the actual electrostatic scattering is. Ultimately, this is a scattering between a charged particle and another charged particle. We're not going to look at that. I'm going to look at a particle coming in, you know, a BB approaching a marble and bouncing off the marble. Now, what can we say about that? And we'll talk about angular momentum and a lot of other important things that are necessary when you talk about scattering. We will eventually figure out how big atoms and nuclei are. So you got that going for it. Any questions about this so far? We want to know more, and so now we need to start thinking about the nature of the interaction. Particularly, we now know that the scattering, I think, well, we'll find out. We're going to look at how the scattering changes as you go around, and that's ultimately how we're going to find out things like, are these BBs or are these charged particles interacting the way Maxwell said? Are they finite sized? Are they this big or are they infinitesimally sized? And so on. That's where we're headed now. Any questions? I will be making reference to some parts of those notes that I posted that I hope you looked at but didn't study. So here's my target. Now it's more massive because we figured that out just by knowing that these particles bounce straight back. We now know these are more massive. That's a particle with an incoming velocity. I guess I changed my notation a little bit. An incoming momentum put my z-axis in this direction. So now, more traditionally, the angle measured down from the z-axis is what I've been calling theta. It's called the polar angle. And so we're sort of setting up to do this in spherical coordinates. I'm going to follow that path. Going to strike there. So in that notation, look down where it is. So it's the notes that start LEC 20-21, etc. And this is slide number 5. And 7 are worth referencing. I'm kind of following his notation. For reasons that we will talk a little bit about, there's good reason to think that this angle of scattering there is the same as the angle of incidence. So what have I done? I have a spherical particle. Why? Everything in physics is spherical. There's a radius, that's the perpendicular to that. This beam is moving in that direction, so it has an angle of incidence of theta. Its angle, the angle it makes with the perpendicular is alpha. For reasons that, again, that we're going to talk about, it's going to come off at the same angle. And so my scattering angle that I called psi before, but that this set of notes calls the scattering angle theta, this is why I don't share my notes with students. I have enough trouble keeping track. That's the scattering angle. So that's what you can measure, right? I can't measure any of the stuff I've just drawn for you. I have no idea how big this particle is because that's the point. I have no idea where this particle is going to hit my target particle. How far away from that through the middle line. I have no idea what this angle alpha is because I have no idea what that normal is. The only thing I can measure is particles going that way. I can set up my experiment that way and I can measure where they come off. And so I got to keep in mind that all of this is modeling to try to tell me what's going on in here. It's almost like the reverse. In experiments, you have the particles going in, you have the particles coming out, you know what the scattering looks like, you have to figure out what's making them do that. In theory, you go the other way. You say, okay, here's what my thing looks like, here's my model for the target particle, what's that gonna make those look like? And you gotta make those match. So if the theory and the experiment don't match, what happens next? I'm gonna keep on, but just while we're here, what happens when the experiment, where you measure the beam coming out and you measure the beam going in, doesn't match with the theoretical calculation of what you bounce out?
Gotta revise your theory.
According to the experimentalists, yes, you did the calculation wrong.
Some people check to see if their experiment was done wrong.
The theorist says, no, you did the experiment wrong. And they both have to go back. No, I've done, I double checked the calculation. No, we checked the calibrations, blah, blah, blah. You interact in that way until they do agree. So you've got to, everybody has to face the criticism that comes from, you did your part wrong. Make sure you did your part right. Fix it if you find something wrong. And then eventually they'll agree. And what do you do then? Very quick millitime, and then you move on to the next project. You celebrate, yay, but basically move on. And you stop arguing about it. That's one thing. That's the nice thing about science. Once we figured out that protons are about 10 to the minus 15 meters across, nobody says they're not 10 to the minus 15 meters across any longer. Politics, they pretty much do that. Pretty much, there are no facts that matter. We at least agree on a set of facts and then move on. So, theta, beam goes that way. To justify this, we're going to talk about angular momentum. And in fact, that turns out to be an important idea because we're going to talk about this classically, the way you would think if the world were made out of tiny little BBs and larger BBs. But in fact, we know that quantum mechanics is the name of the game for this. And you have to do these kind of calculations in quantum mechanics. But in quantum mechanics, this idea of angular momentum is also crucial. It's harder, right? It's a harder thing to calculate than what we're going to do now. But the idea is fundamentally important still. So, does anybody remember how to calculate the angular momentum of a particle? R cross P, very good. R vector cross P. What is P? Who remembers what P is? It is the momentum, he said very quietly, so only I could hear, possibly Kara. And what is R? Right. You don't know what R is. R is arbitrary. You pick it and decide what it's going to be. So let's do that. We're going to take this particle, which has momentum P. We're going to start R there. R is going to be somewhere parallel on the line that's through the center of the scatterer. and parallel to the momentum of the impact particle. Here's my R. So let's do that. Tell me what to do.
Magnitude of R, magnitude of P times the sine of theta.
Well, not that.
Not that.
Oh yeah, I can use theta. No, I used theta already. Nope. Sine of your favorite symbol. No, it doesn't have a favorite. You left them all in. Gamma. You left gamma. I was gonna draw a capital gamma, but I realized I don't know what a capital gamma looks like. Gamma is the angle between R and P, so it's that angle right there, but it's also that angle. So if I calculate the magnitude of this R times the sine of that angle right there, what have I calculated? If I multiply this hypotenuse times the sine of that angle, what have I calculated? The opposite side, this side right here. What do you want to call that? Everybody calls that B. It's too late, somebody already picked a name for that. B. What if I'm here?
B's the same.
Still B, right? Wouldn't it be the same? Would the angular momentum, let me say that again. Would the angular momentum not be the same everywhere along this particle, this path? Would it not always be MVB? R sine theta is always going to be B. P is just M times V, so all I did is write down the magnitude of P as M times V. So in fact, the angular momentum of that particle is the same everywhere along there. Does that make sense? Does make sense? Why?
Just does.
It just does. Because that's the way it ought to be. That's the way the world works. Science works when things are true because you want them to. Why would it make sense for the angular momentum of that particle not to change anywhere along that path?
Momentum's constant.
The momentum's the same. That's true. How do you change angular momentum? What do you have to do to change the angular momentum of anything?
A force.
A force. True, strictly you need a torque, but torques start with force. You can have a force but no torque, but not the other way. So you need a torque. Do we have a force on this particle anywhere along here? Is it going in a constant speed in the same direction? Yes. What does that mean about the forces on it? Can't be any. So if there's no force, there can't be a torque. So in fact, this had to be true. It had to be that the angular momentum was the same everywhere along that path. The only place it might possibly change is here, and we're going to find out it doesn't. There is a force, but that force will exert no torque, at least under certain circumstances. We're going to see what those are. What's wrong with that?
There's no direction.
There's no direction, right? You need at least one direction to tell me the direction of that L. And in fact, what is the direction of that L?
Is it
What
into
hand
the
would you
board?
use?
Is it into the board?
That's what I get. In half. Everybody okay? And it's the same everywhere up to there. And in fact, it depends on this parameter that tells you where it's going to impact. So this parameter that tells you where it's going to impact the target, what's a good name for that? Parameter. Yeah, that's exactly what they call that. They call that the impact parameter. It's this thing that tells you where it's going to hit that particle. We can already kind of intuit what's going to happen to that particle as B changes. So tell me, what do you intuit is going to happen to the incoming particle as it bangs off of that incredibly massive target as I change B.
Scattering angle's gonna change.
Certainly gonna change, right? What's the scattering angle gonna be if the impact parameter is 0?
Right back.
Ought to come straight back, ought to get a 180-degree angle of scattering. As I go up, what's gonna happen? Ought to get smaller, right? As I increase B, the scattering angle is gonna get smaller. There's gonna be a minus sign in there that we're just gonna throw away. That's a very general statement, that as you increase the impact parameter, you decrease the scattering angle. What's the biggest B can be and have some scattering? How large can B, I don't know how to get out of that. I don't know how to not say B twice.
The radius of the large particle.
Yeah, the target particle, if the impact parameter is larger than it is, it misses, right? So there's not gonna be any scattering at all. So that already tells. So you can see sort of how we're gonna figure out what the size of this particle is by looking at where those things scatter to. We're gonna do a bunch of math, but that's really where we're headed. Everybody okay with that? I want you to do this. I want you to show that the angular momentum of this particle calculated about this same point is the same, the angular momentum of this incoming particle after the collision is the same if and only if this angle alpha is the same. I'll give you a hint, and you'll need to talk to each other, and you may need to talk to me. This is kind of a subtle question. It's not hard in the sense that the math you need is nothing that you haven't seen before, but it's subtle. You will have to think hard about it. I don't think it's an easy question. I think it's a hard question, but it doesn't involve a lot of highfalutin, heavy-duty math. So, how can I calculate the angular momentum of this particle and show that it is the same as coming in if this angle here is the same as that angle there? That's your task. Tell me this. Where is the force on that incoming particle? Where is there a force? Let me start again. Where is there a force acting on that incoming particle?
Initially.
Not initially. Only at the impact, right? Only when they bang into each other. What do I mean by bang? They exert forces on each other. And where do they exert those forces? Right here. So now I have a force, don't I? And why is it obvious that there's a force? What's the velocity? Say again?
Change direction.
Yeah. I have this velocity, now I have this velocity. Even if it's going the same speed, it doesn't matter. It changed its velocity. There's clearly a force acting on it. I can even figure out roughly where it is. But, so there's a force acting right there that changes that velocity and yet exerts no torque. How can you have a force that exerts no torque? Over here, no force, so no torque. Check. Out here, no force, no torque. Here, plenty of force, still no torque, because the angular momentum here is the same as the angular momentum there. How can you have a force and yet have no torque? How can I write torque, he said, right next to the angular momentum equation? I think you said R cross F. I actually don't. I wasn't sure. Yeah, it doesn't matter. That's where I was headed. R cross F. In fact, you define these because from Newton's second equation, this is how you find out that this is the thing that's conserved if there's no torque. You start with Newton's F equals dp dt, you do r cross both sides, and you get this. That's the torque, the thing that changes momentum. How can you have an R and an F and yet still have no torque?
Just because B stays the same?
Okay, your evidence for that is L stays the same. But I want to know, how do I get 0 out of this equation? You're going to find out that this L is the same as that L. You will there conclude that there's no torque, and yet there is an R and there is an F, but
I was gonna say the angle between them.
the angle between them is 0 or pi, 180. So the force and the radius have to be parallel or opposite one another, about this center point. That's kind of where we're doing everything from. That's called a central force. If the force is along that line, either out in the same direction or in, that's called a central force. And a central force exerts no torque and therefore doesn't change angular momentum. Does anybody know other example? This one, right? This case where there's no, we're going to find out, parallel component. There's no friction, in other words. We're going to find out that there's no friction at that interface. That's a central force. It acts only perpendicular to the surface. There's only a perpendicular or normal force. There's no parallel frictional force. What other central forces can you think of? Gravity's one. So in fact, orbits have constant angular momentum. Equal areas and equal times, you've heard that one? That's essentially constant angular momentum. That was proof that it was a central force. What else?
Isn't it like when a car is driving in like a circle? Like, we talked about it like engineering mechanics, like a car.
In a circle, that was a center. Okay, so that's good. I think you're thinking of a centripetal force, and that's a force to the center of a motion. Yeah, sounds very similar,
Yeah.
but different. So that's an unfortunate choice of terminology, but on our part, not yours. What else? I mean, there's only 4, right? When it comes right down to it, there's only 4 forces. You already told me one of them, gravity. What else?
Electromagnetic force.
The electromagnetic force. The electro part of the electromagnetic force is central, but the magnetic part of electromagnetic is not. So that's kind of a fly in the ointment. What else? The weak and strong nuclear, and that's kind of what we're here to do, right? We're going to talk about the weak and the strong nuclear. Turns out the weak's not really even a force in the sense of a push or a pull like you're used to thinking of. The strong nuclear is, and it's also a central force as near as we can tell. But, so there you go. All the fundamentals are all central forces. Hence this idea of angular momentum being such a big deal. Where are we? So we did that. We found out this L. You're going to show me that if this alpha is the same as that alpha, then this L is the same as that L, and the force is central. That means that, so that's what you're going to do. You're going to show that this angle and this angle is the same if this L is the same as that L as measured around that center point. Essentially what you need to do is find out what the impact parameter would be for this particle had it come from down here someplace. That's really what you're going to have to do. But when you understand that part, you'll know how to do it, so I didn't really give anything away. I'm going to erase all this. Now I'm going to draw where these two hit. That's that radius. That's the radius to there. And if this angle of incidence is the same as that angle if that scattering angle is the same as the angle of incidence, then that force is perpendicular or central. To change the angular momentum, there's going to have to be a parallel component. Now, we've already talked about that in 221/3. If you took that course, they talked about perpendicular forces and parallel forces. They didn't call them that. Instead of calling the perpendicular component of a force of contact the perpendicular force, what did they call the perpendicular component of a force of contact? The normal force, right? Like the other forces are abnormal? No. That's an old-timey word for perpendicular. There's no reason not to call that the perpendicular component. What did they call the parallel component? It's the force that sent me forward then. Not gravity. Gravity can't make me go sideways. What force makes me go sideways? What force moves your car forward?
Friction.
Friction. The parallel component of a force of contact is friction. So if I'm going to change this angular momentum, which is to say change that angle, I need a parallel component. And that's what I've called friction in the past. The only thing is I need a change, a force that's parallel. Now, what happens if the frictional force were that? The force on this particle from this object had a component that way. I'm not even ask you to think about why that would be. I'm just saying, what if? What if it did? What did your intuition tell you about that angle right there? I think it'd get a little bit bigger. So while you're working on showing that this angular momentum is the same, I need you to think about whether this angular momentum is bigger. That's where it would go. That's where it actually does go. That's a larger angular momentum. So if this big, massive target exerts this force that way on the impact target, what does Newton tell you the impact particle will exert on the target particle? Now tell me this. If this is R and that's F, that tells you you have a torque N. R cross F, torque N. It's going to cause a delta L N, and that's going to make that, it's going to add torque in an angular momentum N. Now, I have too many arrows. I need to erase that and draw the forces that are acting on this particle. So I need to erase that. Is that okay with everybody? Not everything, I'm going to leave most of it there, but we're going to talk about the forces that are on the large particle. So what does Newton tell you the forces on the large particle are going to be?
Equal and opposite.
Yeah, so there's going to be the same force this way towards the center. We talked about that before. That made that made the target particle move in the other direction. Here we haven't worried about that at all. We're just looking at the impact particle. There's going to be a frictional force that way that's going to cause a torque on this object in which direction? Out. R cross F out. So the torque is going to be opposite. that is a torque. That force acting at that same location tells me that I'm gonna have zero net torque on this whole system. So if I'm gonna add or subtract angular momentum from the impact particle, I've got to add or subtract or add the same amount to this particle. Angular momentum is gonna be conserved. And so if I need to worry about changes in this angular momentum, that comes about because I'm changing the angular momentum of the target particle. That's just another layer of difficulty. We're not going to belabor that, but know that that's an important part of understanding what's happening in the scattering experiment. You had a question or comment?
What is that? It's like the B mean at the top? Yeah.
That is the velocity of that particle, which would normally go this way
Would it-
and was just thrown a little bit in
Will
that
it
direction.
change if it's going, if the velocity is going in the opposite direction? Or not the velocity, but the friction's in the opposite
Yes,
direction?
yes. And so if this friction, if the frictional force on this particle were that way, it would cause a different result.
Okay.
And that would, I would either increase or decrease this angular momentum. I would then necessarily do the opposite in magnitude and direction to this one. This is an internal force that acts at that location.
Yeah, I was just wondering if it got smaller because I know in the other instance it got bigger.
So the angular momentum got bigger in this case. If it
Yeah.
threw the other direction, if that scattering angle were smaller, if this angle were smaller than that one, then that would be the other drawing that I didn't make. And we had enough arrows there that I didn't want to subtract more. So I have an in angular momentum. If I make that larger, also in, then I've increased the angular momentum of this particle in, and that means I necessarily have a corresponding angular momentum for this particle out. And all of that still stands. All of those ideas still stand when you do the really hard work of quantum mechanical scattering of particles. It's just, in fact, angular momentum is almost the most important thing that you do, because you no longer are able to talk about an impact parameter, but you can talk about an angular momentum. Any questions about any of that? So, now have some idea of what happens in the middle there. As we're scattering these things, we know angular momentum, or you believe me that angular momentum is an important part of that. Ultimately, what can I measure? I can measure how many particles are moving this way per unit area of flux. That has different meanings in different contexts, and so don't get used to flux meaning one thing. It can mean more than one thing. But in this case, it's the number of particles incident per unit area. So if you think about it, that increases the probability that somebody's going to bang into one of these particles.
Does the numerator have units?
Does the numerator have, it does not, it is a number, very good. But this has units of area, so this has units of 1 square meter. Later on, that's gonna pop up on top, and we're gonna call the thing that results an area, even though it isn't necessarily really an area. So flux is number of particles. Let's do this. In hindsight, we know about how big an atom is, and in hindsight, we know about how big a nucleus is. So let's ask ourselves what fraction of the area, say you had a single layer of molecules, right? One layer of gold atoms, so-called monolayer. They couldn't do that back then, but they can do that now. Got a single layer of gold atoms. I want to know what fraction of the area has stuff in it. Now, one thing, I'm sending cannonballs at it. This electron is in no way an impediment to that cannonball. So it's going to go right through the electrons like they're not even there. But it's not gonna go right through that gold nucleus, because that gold nucleus is like, what is gold? AU, gold stands for AU, how ridiculous is that? So 200 over 4, 200 over 4, 8? No. What's 200 over 4?
50.
50 times the mass, right? This object here is 50 times the mass of Rutherford's cannonball that he was sending at it. So now we're not freaked out that it bounced back, right? It's 50 times more massive. Of course it bounced back. But what fraction of them see one? So what do we know this distance, in hindsight again, what we know now, not what they knew at the time. What do we now know this distance to be roughly?
Is it, 10 to the minus 10?
Yep. An
Meters?
angstrom, which is falling out of favor, or 10 to the minus 10, a tenth of a nanometer, be okay. 10 to the minus 10 meters. And this, anybody happen to know that one?
10 to the minus 15?
It is 10 to the minus 15. And again, we're building up to how they know that. So, what fraction of the area is stuff that you can bounce off of? It's 10 to the minus 15 over 10 to the minus 10. Is it 10 to the minus 5? Is it 1/100,000th? No, it's the area, isn't it? So it's that squared. So it's 1/10 of 1 billionth of that. So you've got your, your rat-a-tat, you're sending these huge fluxes of particles per unit area at this thing, and 10 to the minus 10 of them, 1 in every 10 billion, even sees anything. So that's why you want really bright incident fluxes. You want a lot of this, as much as you can get, right? The more of these you get, the more we're gonna see something and bounce off. So that's why this flux matters. Because if you send 1 billion of them, one here, one over there, one over there, one over there, it doesn't really matter. It matters that you have a whole bunch of them in a concentrated beam. So that's why that matters on the incoming end. Then I measure the number scattered into d omega. Who knows what capital omega stands for? It's a trick question, right? Could be anything. But in almost every physics class I teach, I try to be very careful and not use omega for anything except this one thing. Who knows? Anybody? Classes for me before? Recently? You're in the clear, right? You're in the clear. Well, okay, it is the unit of resistance. Okay, so yes, I do use it in another context, but that's not my fault. Anybody happen to know what you get if you take this arc length and divide it by that radius? If I take that arc length, S, and divide it by that radius, what do I get? I get an angle. It's pretty clear that the bigger I make S, the bigger this angle is. I don't want to call it theta because I've been calling everything theta. What's your favorite? Gotta pick.
I don't know.
It's okay. It won't affect your final grade.
Can we just use a letter? Sure, A.
A. A is that angle. But measured in what? Radians. That is radians. Now, what would it be if I took that area of that panel the area of that panel and divide by the square of the distance between me and that panel.
Is it steradians?
It would be an angle omega in steradians. And if you know anything about why they call it steradians, I would love to hear it. Anybody, right? But if she's in the business, she might know. So that's an angle. How do I distinguish this angle from that angle? I call this one a solid angle. It's like, you know, theta and phi, right? Two angles. In fact, you can relate it to spherical coordinates. I'm not gonna, but you can relate it to spherical coordinates. And it's related to the azimuthal and the polar angle. But ultimately, it's the area of something divided by the square of the radius. So tell me this. If I go all the way around this circle, what is A? What is my angle? If I go all the way around this circle, S, what is my A? 2 pi, right? This would be 2 pi r, the r's cancel 2 pi. A would be 2 pi if I'm all the way around it. 2 pi radians in one full circle for that reason. If I go everywhere in all directions, how many steradians is that? Well, imagine that I'm at the center of a sphere. I don't have to be. Steradians are fine, even if you don't have a sphere. You don't have to have a sphere to have steradians. But if I'm inside the middle of a sphere, and I look everywhere, what is the area of that sphere? What is the area of a sphere of radius r? It is not pi r squared, but you're most of the way there. She wants to say it, but she's not gonna. Four of those. You were gonna say that? Should have said it. Now all we have is your word.
I didn't want to be wrong.
You want to be wrong? Yeah, never want to be wrong. That's the way to be successful in science. Never say anything that might be wrong. Be the I in team. Who's heard there's no I in team? Be the I in team. Be the person in the team that says, hey, wait a minute. Here's what I think. And if you're wrong, you're wrong. If you're in a good team, being wrong is going to be okay. If being wrong is bad, find another place to be. Because that group is not going to make it. If you don't find errors, if you don't fix problems, be the I in team. 4 pi r squared. So how many steradians if you go in all directions? 4 pi. Still 4 pi, right? What if you're in the middle of a cube? Still 4 pi, right? Doesn't have to be a sphere. There's still 4 pi if you include every direction. Tell me this. You're in the middle of a cube. How many steradians in just one side? Figure that out. Figure out omega for one side if you're in the center. Then do it if you're really close to the opposite side. Still inside, but really close to the opposite side. Then do it when you're really close to that particular side. How many steradians? Finally, figure out how many steradians that panel of the board, one panel of that board, subtends if I'm here. What is the steradians of that board? That's enough. When you get done, when you come back next time, you will know steradians if you do all those things that I just asked. And then we're going to talk about detectors. We will, in the fullness of time, I promise, actually scatter something and actually figure out how big it is. Right? Are we not done?
I think we have 15 minutes.
Oh, dude.
16.
I thought we were done. Okay, that's why you give me that look. Okay, everybody's okay with the assignment then? I was trying to rush because I thought we were, I'm getting used to my new schedule. Everybody's okay? If you have any thoughts or any questions about that, you ask me and we'll figure it out. But what are they? Find how many striations that panel. Find the solid angle subtended by one side of a cube if you're in the middle. If you're on near the other side, near the same side. You can imagine that they're probably different. So now we know that. Tell me this, what are the units of radian?
Unitless.
It is a unitless number. How do you know it's unitless?
That's what they said when they made it.
I told you that, it's written in a book someplace. What are units of X? What are units of R?
The same.
Doesn't matter, but they have to be the same, exactly. So those units are going to cancel. So this has a name because it's important enough to have a name, but it's a unitless number. What about the units of steradian?
Unitless.
It's going to be unitless. So, Mr. Check the units, and that's how you can tell if you're doing it right. Yeah, this is the bane of my existence. Steradians don't have units, so you could have screwed up and you would never know. Unless you get some units, in that case you might have screwed up. All right. So we have these incoming flux, and I'm following the same notation of that textbook, and so those are, I think he calls it J incident. I don't really know why, but it's a perfectly fine unit. Oh yeah, there. They scatter off the stuff, and then you have a detector over here which has a certain solid angle with respect to whatever that scattering region is. You got to figure out where the scattering region is, and you got to aim your detector at it, and your detector has a certain solid angle extent. And you can count the number of impactors that bang over and hit your detector. That's essentially what you can do. You can count that. Back in the old days, you had to actually sit there with a microscope and count them, right? Go blind. Now we have the machines that do that for us. But you can now talk about the number per unit omega, and that's going to depend on this angle theta. In principle, right? We're going to look at whether it does or not, but in principle, you can get a different result depending on where you are. So I have particles that come in with a certain impact parameter B, and they scatter at this direction and hit that detector. But if their impact parameter is ever so slightly different, dB, they also hit the detector. Because your detector is not infinitesimally small. If your detector were infinitesimally small, that'd be great. You could point it in exactly one direction. The problem is, nothing would ever hit it. It's too small. So you have this competition between, I need it big enough so that things hit it, and I actually get a signal I can measure, but it's so big that I can't really tell which direction those beams are really going, so you can straddle that. So between B and dB, I have a certain number of particles that actually hit my detector within that range. And so there's a number per unit steradian, could possibly be different for different angles, times steradian, that arrived at my detector between B and dB. And that's going to be the number incident per unit area times the area of that ring. and that's gonna be 2 pi b dB. And now I'm gonna tell you to look at that lecture 20-21 PDF. I think that's either slide 5 or 7, it's one of those, but all through in there is what I'm doing right here. All I'm doing is copying what they did. And so, if I call this ratio the number that hit my detector divided by my incoming flux, that's called the scattering cross section per unit solid angle. So, size of my detector, I'll give you a second. This is me just taking this ratio over that ratio. This is a definition. I'm defining this thing d sigma here. The whiteboard is my detector. This d omega is the solid angle of my detector. And so the bigger that is, the more particles are going to hit it. The more particles I send in, the more particles are going to hit it. So that's why you expect that proportionality. That's why you expect this to be tell me something. Because if all I do is send in a beam of stronger and stronger particles, yeah, I'm going to get more detections. I really want to know, how do my detections compare with what I sent in? That's what this is about. What fraction of the particles I send in bounce and hit my detector? I call that the cross-sectional area per unit solid angle. Solid angle is telling me how big my detector is. This is something called the scattering cross-section. Why do I call that a scattering cross-section? What are the units? Look at this, tell me what the units of sigma are, because you already know what the units of d omega are. What are the units of d omega? Doesn't have any. What about that? That's a number, it's a counted particle, right? So no units, no meters or anything like that, it's particles. What's J?
Also,
Say again?
also counted now?
It's not just a number.
It's 100 meters squared.
Yeah, it's number per unit area. It's how bright the beam is, how many particles are coming in per unit area. And that's related to, I want them to be able to find that nucleus. So, if this has units of 1 over area, what are the units of this? Area. So what are the units of this thing on top? Because that's unitless, this has units of area. So you can think of it in terms of sort of from the perspective of something coming in to bounce off, how big is it? So we're gonna find some things that are not gonna surprise us when we think about what this is really measuring. You do that math, you get B over sine of theta times dB d theta. That came about by writing what d omega is, and I'm not gonna bother you with that. It takes us someplace we've already done it. It has to do with spherical coordinates, and they're important and they're fine, but we're full. So you're just trusting me on what this is. You're not trusting me on what it represents. You're not trusting me on this definition. You're just trusting me it turns into this in terms of scattering angle and impact parameter.
Do they have that in the lecture?
Say again?
Do they have that in the lecture?
They talk about it. It's in the textbooks, and also it's in those PDF files. They talk a lot about it. So anybody who wants to dig in, absolutely dig in. And I'm just not gonna hold you all responsible for it. Anybody wants to learn it, I'll absolutely explain it to you. So let's go back now that we know sort of what our experiment's gonna be. That's not it. We go back to our particle, there's B, that's theta, that's alpha. We know that B equals R sine of alpha. And again, this is on those notes. You really don't even have to write all this stuff down. I know that theta plus 2 alpha is pi. That's going to help me relate alpha, which I care about but can't measure, to theta, which I can measure, but isn't the thing I really truly care about in here. So that tells me B is R sine of pi minus theta over 2 alpha. No, not theta, I did that right. Which he gets a minus sign that I don't understand, so I'm happy for somebody to figure that out. I don't get a minus sign. He shows a minus sign in those notes in that PDF that I'm referring you to, that I posted for you guys. If you can't see the stuff I posted, let me know, because we got to figure that out. It'll be easy to figure out. I just want to know if that's not a good way for you guys to get information. Anyway, he gets a minus sign there. I don't. dB d theta, just take the derivative of that. You get minus R over 2 sine of theta over 2. So my experimentally measured thing is R cosine theta over 2, which should be a capital R. That's B over sine of theta times what we just calculated, minus R over 2 sine theta over 2. So I've got a minus, I got an R squared over 2, I've got a sine theta over 2 and a cosine theta over 2. And I write sine of theta as twice sine theta over 2 cosine theta over 2, which you're not used to seeing. You're used to seeing sine 2 theta equals 2 sine theta cosine theta. It's one of the double angle forms. Reason for doing that is you now wind up with minus R squared over 4. So the change in scattering cross section as I go from here to here, it's constant. Right? Depends only on the size. But that's pretty nice. If I now measure my scattering as a function of that angle and see it not change, that tells me, oh, that's a hard, impenetrable sphere that I'm bouncing off of. I have BBs that are bouncing off a marble. And in fact, if I measure it, I add all those up, right? So I do my, what's called the total scattering cross section. I integrate this, and I'm not going to show you that either. Sigma is the integral of d sigma d omega, that's this, the differential scattering cross section, times d omega. Everybody okay with that? Mathematicians, close your eyes, because the d omega cancels. We know they really don't, but we play like. So that's going to be the total scattering cross section. That's me adding up all the scattered signal that I have. Well, what do I get? When you do the work, you get pi r squared. Which doesn't make much sense, right? Because pi are round, cornbread are squared, but I'm sorry. What is pi r squared? It's an area of a circle, right? It's an area of a circle of radius r, but in this case, it's the cross section of my sphere. What do I now know by knowing what fraction of my incident particles scatter into somewhere onto my detector? Like go through and try them all out and then sit there with the cipher, do the ciphering, add them all up. What have I now figured out?
How big the sphere is.
How big those are. That's pretty good. That's how I know 10 to the minus 15. And you can see there's a lot of work involved, right? Every sentence in a book, pick up a textbook, every sentence, virtually every sentence, somebody's life was in that, right? That's how they got their PhD. That's why we now get to say that. Every time you pick up a book and they say, yeah, protons are 10 to the minus 15 meters across. That's what it took. And you get better toys and more tools and you can figure out more stuff, but it's still, somebody's got to sit down there and grind through it. A lot of tedium in science. Who's got an advanced degree of any type? Yeah. Mostly you just loved it, right? Nothing but joy, every sentence. Yeah. But it was worth it, right? Because there was enough, yes, buried amidst all the, man, this is terrible. I gotta get out of here. So, it needs to be the case, right? You need to care about it enough that you're gonna stay through the horror. Goodbye.
Good luck.
How are you doing? Next, we will talk about when it's not hard sphere. We're going to talk about what does it look like. We're not going to do the calculation. We're going to look at what is the result if it's an electrostatic force. So that's what you look for. And then if it's an electrostatic force with a finite size. How do we figure that out?